We are building the standard model. The trouble is, you know, I'm making a drama out of it, and you guys know it, it seems, most of you. You sort of, you know too much. Right? I can see when I talk to you guys, some of you read online or have heard before, you know. It's good that you do that, but you also beware, you know, I have to do a warning, okay? It's not good to know too much too early, because then you often, you know, get a feeling that you know. So I'll start from scratch once again. What we said last time, remember, we had to choose the Higgs. After all, we know what the standard model is, right? There is a standard model gauge group. It's an SU2L cross U1 symmetry, which I have to break down to U1 electromagnetic with a vacuum expectation value of some field, and obviously what I'm breaking is SU2. And now why am I making this, you know, thing a drama out of it? We already seen in the SU2 example that the doublet does the job. Right, there is a strong indication. What we've seen also something very interesting with the doublet. So when you do the SU2 cross U1 breaking, your homework problem with the doublet, what you notice, this surprising thing that although all the symmetry is broken, the masses are the same. Now this is not a situation in nature, right? W and Z masses are not the same. So now you could even, you could doubt, is this going to work, right? Because there is a tendency to produce it. But what we know, however, in nature, that they are quite close. Well, now I'm just going backwards, you know, historically we didn't know anything, okay, so we wrote a doublet, okay. So maybe it could work because there is this sort of U1 entanglement, right? The U1 that I end up with is not the U1 original. Something is going on there, right? Which is kind of screwing up. It's confusing the issue, okay? All right. We could be right, we could be wrong. But what was very important, I know, in other words, the doublet will do the job of giving all the gauge bosons the masses. That's good. I have to make sure the fermions get a mass. Okay, we studied it last time. We actually showed it. If I can simultaneously give all the fermions the mass, then of course it's a great achievement with one and the same Higgs. We would do a complete job. So what we said, there was no way of writing the masses right. What is important when I define a theory, you define the gauge group, then you define your protagonist, what we call matter, our usual left-handed doublet. ER. Okay, we've never seen UR, remember, so though there would be a dilemma whether or not to put it, since we haven't seen it, okay. The fathers of the standard model decided to stay minimal, okay, a natural thing to do. And then we notice we can't write the masses, just like all other fields. At this point, we are massless. Why? Because a mass is a left-right term, and I can't give a mass to a doublet and singlet simultaneously, right? All I can do is I can write some Yukawa, QL bar, dr, we said. Naturally, I put a doublet here. And this is great. The hypercharges work out if this hypercharge is 1. I could have defined the hypercharge here, but we already made a convention. So now it follows. Okay. That I call Yukawa D because it's down quark, which is important. There are 2 of them here, but down quark is here. And then when I wanted to do it for the up quark, I couldn't do it, but it was easy to correct. If instead of phi, I put a field, which we called phi tilde, the virtue of phi tilde, of course, is phi is a doublet, U is an SU2 transformation, then so is phi tilde. And I was showing it in various ways. I should have done it really, because you knew this. You know actually much more than this. In your first homework, remember when I keep telling you, if you know SU2, you know everything. For example, Lorentz.
What is phi tilde?
This.
Oh, okay, fine. Sorry.
It's all right. Okay. Make it. For example, Lorentz seems so different from SU2, right? But imagine that you and I were to live in the Euclidean space. Imagine that the time where, like space, it would be strange life, right? But at least we could go back and correct for our errors, right? We could move that we had to do in space. So Lorentz, which is not, but becomes SO4 in Euclidean, right?
Yes.
And I hope that some of you know that this is, I hope that all of you know, I know that some of you know, it's actually equal to SU2 plus SU2. And it's not surprising when two groups have the same rank and the same number of generators. It's hard to imagine. There is a complete classification by Cartan, right? And then there is uniqueness of this group. But this can be shown explicitly. Anyway, what you've shown, remember that if psi is a spinor, so is psi c. Okay, small digression just to show you that you actually knew this. It was a big deal, right? This is this famous thing of Dirac, right? If there is psi in the field, there is psi c. If there is a particle, there is antiparticle. After all, this is a complex conjugate. This describes if this is an electron, this is a positron. What was psi c? C psi by transport. What was this with our matrices?
I sigma 2.
I gamma 2,
I got
psi star, which is actually I sigma 2. After all, if psi is u,
yes.
well, let's use our usual notation, ul and ur. What will be psi c? Is I sigma 2 ul star up to a sign. Maybe it's upper, lower. Overall sign, who cares? Minus I sigma 2 ur star.
There is not a phase.
Well, we could put a phase, but there is no phase. This is how I define psi c. This is my c. My c is I gamma 2 gamma 0. So notice you already done it, okay? After all, this is ensuring that this behaves correctly under rotations, okay? When you take I sigma 2 u star, what is SU2? It's rotations. Okay, well, rotations of spin. So you know that, really. And it's important thing for you to have this sort of thing, this connection between SU2 and all the other groups. For example, the Lorentz generators, which are sigma mu nu. No. I can write them, but I don't have to. They break down in rotations, right? Which came out to be sigma I over 2. And if you write in 4 components, because as you know, these poles are spinors. Transform equally under rotation, they carry spin 2, spin half. And then there are boosts, so this is rotation. And then there are boosts, Ki, which have I. And the difference is that left and right are sort of opposite. We keep saying that. This is why I distinguish them, okay? When left moves left, the right moves right, if you wish, okay? There was this helicity thing that we found out between left and right. Remember that right guys have opposite helicity, okay? You check that. So,
what is the other matrix?
sorry?
Is a spinor? Is a vector? What is the?
What? Who?
What is in parentheses?
In parentheses.
Yeah.
Here.
Yes.
No, because it's a.
You're applying the.
This is 2 by 2, but it's 4 times 4, Lawrence.
You're applying to a rotation to a spinor, or what?
Yes, these are the generators, right? The generators, sigma mu nu, are 1 over 4, right? Gamma mu, gamma nu. So there is sigma 0i, and there is sigma ij. The sigma 0i is basically ki. The sigma ij is I epsilon ijk jk. These are rotations. Okay, so these are 4 times 4 matrices, obviously generated. So I have to remember that this is plus 1 plus 1.
Ah, okay.
This
okay.
is a unity.
Okay.
Sorry, I'm making it
Okay.
clear. Well, I'm glad you asked. I don't want to leave you confused. really all I care how they act on my spinners, but this is just to remind you that left and right are both spinners under rotations, okay? There is no distinction between them. They only slightly differ, or a lot depends, under both. There is a relative behavior which is different under both, but every spinner is a spinner. So when I say it in the Lorentz group, and notice that my generators are Pauli matrices. I'm always working with Pauli matrices, okay? If you think of gamma, think the way you did gamma matrices. Gamma I, what is gamma I? Pauli matrix. And then what is gamma 0? It's just the diagonal traceless piece, orthogonal, right? So which we compute. Well, it's not the. We don't classify it. This is not a compact group. Lorentz doesn't go into the same classification, okay? But the same thing happens. Why? Why does it work? Because it's almost SO4, which is SU2 per SU2. And the only difference is that boosts are a bit funny, okay? There is a factor of y. They're not Hermitian. Lorentz group has no finite unitary representations. If you want it unitary, that's infinite. If you want it finite, it's not unitary, right? It's not basics of Lorentz group. But for practical purposes, what I mean, working with groups means knowing Pauli matrices. We'll keep running into that. So I can write Yukawa coupling for up quark, and I can write the same for the electron because I will have LL bar phi dr. It's very easy to see that this also works because this has hypercharge +1, -2, and -1. Hypercharge. So I can give everybody a mass, okay? This is a great success of the minimal standard model. One and the same Higgs. Apparently does the job of providing masses to everybody. Higgs, gauge bosons, and the fermions, okay? Why? I know when I do the doublet, then I can always choose the wave in this direction. I'm going to comment what happens if I change the direction, but I can always do that. That's original symmetry tells me. After all, the potential was phi dagger phi minus v square over 2 with my normalizations. Sometimes I notice I put a factor 1/4, sometimes I don't. Don't get confused with that, okay? That's just a convention for lambda.
So there's a whole square?
Everything square. Thank you. Good. If I do that, if I choose this particular web, and I have to come back and comment on that, notice it would work immediately to provide the masses in the vacuum. Why? Because here, notice you pick up a down quark. Look at my doublet. For example, let's just do one of them. U bar, D bar, L, phi 0, dr. Yukawa.
Sorry.
Yes.
What does it mean, like having the
Maybe I want this 1/square to minimize the potential.
What does it mean having the down part with the left hand?
Thank you. I like this politeness, you know. I'm not sure whether you're polite or not sure, actually. You know,
Yeah, always.
I remember my advisor, he was very polite, so I remember a few times I made a mistake. He said, I wouldn't put the, you know, imagine you write the Feynman rule with the arrow here. You say, I wouldn't put it in this direction, you know, when you're breaking. Thank you. What would happen if I put the R here? Many things that will go wrong. Suppose I had written this. Just to appreciate how bad this error would have been. What symmetries am I breaking here? Charge. Let's go on. Charge, that's bad in a color.
Yes.
There will be no SU3 symmetry I'm talking about. There will be no charge, you agree? More. Something very bad for you and me.
Number.
They don't want that. Barrier number, that's even worse. See, because if I violate baryon number a lot,
What is it?
what's going to happen? You and I will decay. No, it's really dangerous, okay? Well, you may say, okay, it may take time to decay, okay? We'll come back to this beautiful issue now that I made this mistake. It's useful. You see how it's, a distinguished experimentalist, my ex-colleague at Brookhaven Lab, Maurice Goldhaber, actually wrote down the first limit on, first useful limit of proton lifetime. He used to say, I feel it in my bones. What did he reason? If proton were to decay, not only that you would decay, something dramatic would happen much faster. Radiation will kill you. Radiation is bad for you. So, you know, if they tell you to take a CAT scan, think twice. Okay, for example, the X-ray may be okay. As we know, a lot of radiation can kill. So this is just a side remark. There is a beautiful limit that hopefully at the end of the course we'll talk about when I speak of the route beyond the standard model. I have to sort of wet your mouth. He put a limit of 10 to the 18 years from the fact that we live, basically on average, say 78 years. It has to do with the number of protons that are inside us, the amount of the radiation that will kill you, okay? It's interesting. I gave a review a few years ago on proton decay, and I went through this argument for fun, okay? And it's impressive. It took them a long time to improve it, to get dedicated experiments. Do you know what is the limit today? So this is just from us. Do you know what the limit of proton lifetime is? There has been a search. Yeah. It's actually 10 to the 34, 35 years. It's much bigger. What would you do if you were to look for proton decay? You take something bigger than us, right? So what is ideal? What is cheap source of protons? Water. You take a swimming pool. The ideal, you would take a swimming pool, sit at the pool, you know, take a swim from time to time and wait for some protons to decay. Now the trouble is you get cosmic rays, so you hide these swimming pools deep down in the mind, but the idea is the same. Okay. Anyway, so much about the side remark, and this will be very disastrous because they're large. So let me not do that. Let me not break it. Notice the emerging feature of the standard model that I can anticipate already. I wish to preserve charge and color at all costs, and Lorentz symmetry. Okay, that's sacred. Okay, you and I are not allowed to touch these symmetries. Okay, we may talk about it over beer or coffee, but not here while we are being, you know.
Which symmetry?
Sorry.
Which
Color. Sacred symmetries. Let's once again. Well, more than that, I have to respect the symmetry of the standard model. I'm allowed to do the Higgs. I can't break the symmetry explicitly because then the theory is not good, not finite, not renormalizable, as we say. So it's SU2 plus U1 and SU3, and very important, times Lorentz. So all my interactions, when I said, you know, I need to write a mass term, but I can't. So I'm going to complete it by scalar. See how I need a scalar, elementary scalar, okay? Because otherwise I will break the Lorentz symmetry, okay? And I want to give them the mass, but I don't want to break color. So I can't put here a quark. I have to put a lepton. I have to put a quark for color. Color, 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 color. No color, no color. You see what is emerging, okay? That although I'm not demanding, baryon number, it seems, and lepton number end up being good symmetries, okay? And that's beautiful because we don't see that in Asia. So somehow the structure of the standard model is ensuring an important fact. Okay, if I write this, look what will happen here. I will get Yukawa over square root of 2 times V, dl dr. But of course there is a Hermitian conjugate, right? Less Hermitian conjugate. Plus Hermitian conjugate. And this is Yukawa V over square root of 2 d bar d. So in the same manner you will get the electromass, obviously. I don't have to repeat for you. This what phi tilde does because of sigma 2. It takes. So when we write it here, phi tilde, that is V0 over square root of 2. So I conclude that the Fermion mass is Yukawa fermion V over square root of 2. By fermion, I mean up quark, down quark, and electron.
Why is called Yukawa? I mean,
Well, this is a historic thing because this is an interaction that Yukawa imagined that will give strong interaction. Okay, we know now that strong interactions don't go like that. There will be interaction between two nucleus generated by a messenger, which was supposed to be a pion at the time, a pion looking like particle. So the form of the interaction is funny, only because of the form. It has nothing to do with the original Yukawa. These are very weak interactions. Yukawa couplings are small, nothing to do with strong interactions, right? It's a completely different picture, but the name stuck. See immediately an important prediction of the theory, the minimal standard model. And we should be really grateful to this prediction. This failure maybe is one of the most beautiful and most important predictions of the standard model. It gave us, you know, bread and butter, and to some of us chocolate or whatever we like. You know, the thing is, because what you and I want is to find failures of the standard model. We want to have fun, right? But especially you guys at your age, right? You want to be part of something new. There is something new. We know, you know, right? Alexei told you. Neutrino is massive. So we'll have to talk about it. When I define the standard model, obviously the minimal standard model is not the whole story. Okay? When I teach the standard model, I have to include whatever is needed to discuss neutrino mass. I have to go beyond to some degree. And it's not clear completely which row. The one which has emerged as a completion of the standard model, it's called the seesaw mechanism, okay, and that we'll have to say a few words. Okay. But at least we have a great success here. And since we studied this potential, you and I know that there are various ways of writing my field. How am I doing? Okay. I have to choose the variable. Now I want to understand what is going on. I want to get as simple and as clear picture as possible. So I'm going to do what is called a unitary variable, unitary gauge. How do I do that? I write phi, let me call it phi prime, as e to the I gi sigma I over v. This is just the SU2, right? I can put a half if you wish. Transformation, but it's also a way of writing. I have to choose the variables any which way I want. So I can write like this, let me convince you. Three Pauli matrices, three fields associated. I know that there are four real fields altogether. Okay, let's check. I invite you to do this mentally. The small transformation, sorry, before doing it mentally, I can write this as 1 plus gi vi. Let's keep this 2 because this looks like an SE2 transformation, plus other terms, higher orders. Do you agree? I've just expanded it. So what do I get? I will get 1 over square root of 2. I will get v plus h here, the first term. How will the, say, where is sigma I written? Not so nice. How does sigma 3 act diagonally?
the same.
So I'll get minus I over 2 G3. Sigma 1 off diagonal. So I'll get I over 2 G1. G sigma 2 off diagonal, but there is minus I plus G2 over 2. Plus higher order terms. Normally this is the way you would have written it, okay, in a funny notation that I've chosen here, but precisely because you yourselves told me that many of you did it in the homework. You wrote this as a phi 1 plus I phi 2, phi 3 plus I phi 4. One of the many ways of you writing. Okay, notice it's the same thing, right? Phi 3 is 1 over square root of 2v plus h. Phi 4 is minus 1/2 over square root of G3 and so on. Identification is trivial, right?
Yes.
It's just real. Imagine because of 1 and 2 sigma 1, there is some name change. Okay. So this is surely a correct way of writing the field because it reproduces the, for large VEV compared to the value of the field, reproduces the generic form. The idea of unitary gauge, remember, is to take phi, which is an SU2 rotation, e to the minus I gi over 2e sigma I. Acting on phi prime. And that's 1 over square root of 2, v plus h. Just to give you one case, I can go to the situation where there is just a Higgs field. Okay. Again, the beauty of the simple minimal standard model. Okay, one Higgs doublet, and then only one field. Okay, the complicated Higgs picture reduced to one field, just like the scalar case we started. You know, you and I know that mh squared is 2 lambda v squared. There's nothing more to do. And whenever I see the wave, I can replace it by h. They go together. This is my field. After all, what is h? That's the excitation around the minimal value, the vacuum value which I chosen to be real. Okay, we could have taken the phase. I chose it here. Okay, let's put this G if you wish for boron. You may not for Goldstone, okay. For boron, okay. This is not so noble, okay. Because you may not like my minimum. I have to convince you that it's a good one. I didn't even have to do this gymnastics. I have the right to write like this. Unitary gauge simply is my freedom to eliminate the phases. So let me use the blackboard. In the unitary gauge, phi unitary, and simply 1 over square root of 2. There are 4 fields, and therefore there are 3 phases, okay, that I can call 1 absolute value and 3 phases, okay, in this situation. So that means, so I get immediately the Yukawa Lagrangian, actually is a correction to the mass. It would look like Yukawa, why not I write just M fermion, psi bar psi, for every fermion. Maybe we give it a name 5, up, down electron, plus Yukawa over square root of 2 H psi fermion, Yukawa fermion, which is nothing but M fermion over V H psi fermion. Where there is a wave, I can put H, so I get this interaction, and this is what I expected without doing any work. I've already learned this by playing with Higgs. Higgs couples to U proportional to your mass, if it gives you a mass. It gives fermion a mass, so it's going to couple proportional to the mass. It is dimensionless. How do I know it's dimensionless, the coupling? Because this gets dimension 4, right? 1 plus 3/2 plus 3/2 is 4. Therefore, this coupling is dimensionless. I don't have to do any gymnastics at all. This had to be M fermion over V. V is the only scale in the theory. The same way that the mass has to be proportional to V. So two things you learn. The mass, if Higgs gives you the mass, will be proportional to the way it couples to you. And then, of course, obviously, the way it couples to you is going to be proportional to mass. It's one and the same statement. Okay. So far, so good. Now, briefly, there are more than just these fermions, right? Although the universe is made only out of this, unfortunately, there are three such generations that we call, right? So, and every time what I did here for one generation, I have to repeat it, you agree? I mean, they're just zero copies of each other. So if you ask me what is the mass of the charm quark, I would say charm quark put the Yukawa charm. If you like some other quark, you say, I believe there is another generation, okay, stick it. Put it, I have no problem, then Yukawa, your top prime, will be mass of the top over V or vice versa, okay, I can do that. To many people it is ugly, even to the father, or at least Leptonic part, was done by Weinberg. It's often called the fermion mass problem. It's sort of asking why are these parameters there, how do I compute them, and so on. I find it beautiful. It's not that I'm not bugged by this. I want you to appreciate here immediately. It's true that I don't predict the masses, that's true. I can't tell you why electron weighs 0.5 MeV. So you may say, okay, but then every time you have this arbitrary mass parameter, okay? Well, there is more to that, okay? There is a sort of a dynamics of masses, if you wish. It's not just numbers. And that is the following, that once I said, and I use it, that Yukawa fermion 1 over square root of 2 is M fermion over V. And you know when the Higgs decays into fermion, F bar, you don't have to do the calculation. You know this will be proportional to Yukawa fermion square. Okay, suppose you're lazy. You can do that. We can maybe have a homework, or you can think, I don't want to, I'm lazy, okay, how would I estimate this? I would say this is going to be Yukawa fermion square. It has to be proportional to the mass of the Higgs. If Higgs is massless, the decay rate goes to 0, massless particle cannot decay. I get the right unit, you agree? And I know that there is always 1 over 16 pi, 8 pi, I'm not sure. Remember from those decay rates that we wrote? Okay, I put some number here. Okay, 8 pi, I think. I don't know. I'm close with this, okay. But this is actually, and I don't care the number, M fermion square over this V square MH. So what I do, for every parameter that you give me, I predict a different process. And I predict the rate. So this is not just the empty picture of free parameters, okay? There is a dynamic associated with these parameters, okay? This is something to appreciate. Because many papers that try to explain these masses do worse than the standard model. Suppose you have some mechanism that tells me why electron mass is 0.5 MeV, but you have no new dynamics. I don't give a damn. What I want from good physics is a dynamical prediction of phenomena. And maybe we should compute this nicely. This is how you and I are going to check the Higgs mechanism. We have to make sure that this goes through. I'll come back to this. Okay, so Yukawa sector was a success. But maybe you can ask me at this point, but it somehow seems to depend where I put the web. If I put it up there, then these guys are not getting masses. Something crazy is happening, right? No? Suppose I put the web here.
Yes, it will be 0.
Well, No, it'll be worse than that.
no,
I will get up, down mixing.
But then you cannot do the same trick.
Sorry?
You cannot do the same trick like putting I sigma 2.
Yeah, well, I could, but you say, well, you wrote it like this.
No.
Why do you take wave in this direction? Okay, well, remember, it all makes sense if my wave doesn't break charge. So I have to ensure that the wave doesn't break charge. But you say, if that depends on your choice, that's a lousy theory, okay? So let's try to see what happens, okay? Let's now, the next step, let me convince you that charge is not broken. I will erase this if you think you copied it. Let's pursue this a little more. After all, how it started, I defined Q as T3 plus Y over 2. Remember, that was my conventional Y. And that works very nicely because I see immediately that Q phi 0 is 0. Let me write it Q electromagnetic. Although every generator, which are Pauli matrices, gets broken, and so does hypercharge, one linear combination remains unbroken. Okay? And that's precisely, you see, it works if I put the wave in this direction. Okay, so I have to put here phi 0 dollar. Who wants this vacuum? Whose name shall we give? The other one. Phi 0. Who is the devil's advocate? Okay, choose. You wanna? Huh? She's looking at us. No, he looks like that. Okay, let's choose him for fun. He says, well, I want to have V0. And then you say, look, notice, Qn phi 0 Vasif would be non-zero. Charge is broken, so who is right? Me or him? Well, I ought to be right, you know, I'm teaching the course. But that's not a democratic decision. I'm being too pedagogical here, but I want to make sure this is, I find this often confusing to people. Well, notice the thing. First, notice the following. This is true, but notice that Q electromagnetic phi tilde Vasif is 0. So actually charge is not broken, because who says you have to work with phi? You can work with phi tilde. They are both doublets. Or, if you wish, if that's not convincing you, then take Qm prime is T3 minus Y over 2. Notice that Qm prime acting on phi 0 Vasif is 0. So actually, no matter how you choose your charge, there will be one linear combination. This is what you call charge. I've anticipated, I sort of run ahead of myself. This definition of charge is good with my choice of the wave. Otherwise, I have to redefine the charge. And the point is that, think of it, you have two generators here which are neutral. They belong to Cartan. You have only one wave, and it's not going to break two different generators. There will be always a linear combination which is unbroken. But you say, okay, I've proven it, you agree, this wave is equivalent to my wave. Because either you work with tilde, or just change the definition of charge, okay? But then you say, okay, phi 0, who is? Who wants to take this? You have to be really sort of nasty to do this. You said, well, in this case, what are you going to do in this case? Which linear combination now is true? It's neither Goran now nor what. I can choose that. After all, the only thing I know that phi 0 tilde, phi 0 is V square over 2, which is equivalent here that V1 square plus V2 square is V square over 2. Well, I could put the square root of 2, so it's just V square. Notice that both Qm phi 0. Well, I should have had a name. This is Goran. And prime is Vasif. Both of them, both Goran and Vasif, unfortunately break this. So it seems the charge is broken. So what is going on? That'd be terrible, because if the physical result, if the nature of symmetry breaking, depending on your convention, okay, that'd be a disaster, right? Everything would break down. Well, all that you know is the following when you start with. When you say that you break SU2 cross U1 to U1, or where you say that inside the theory there is electromagnetism, and that's how you started with. You and I decided to construct a theory for weak and electromagnetic interactions. Not just weak. That's why we needed 4 generators. We started with SU2. Remember, we really wanted this. It was Schwinger's dream that was finally fulfilled by Glashow and Weinberg and so on. And so there is a photon living here among these messengers of gauge bosons. That means that the electromagnetic charge, all I know, is a linear combination of these generators of the group. So for example, if this is 2, I could call this plus Cy times y over 2. In general, it's a sum of all the generators. It's some linear combination. And so what will be, who was this? Nobody wants to volunteer. Whose name? Okay. Hella. Let's choose Hella for this. Okay. QM. Hella would then be. So a little exercise for you. If you don't believe in symmetry arguments, you're not convinced. You don't feel it in your. It has to be in your blood. It can't be that you leave even a trace of doubt. Find these coefficients. It's an easy exercise. It will take 5 minutes. I guarantee you that there will be, you have to solve for Ca and Cy. There is more than one solution. So that Qn Hella acting on phi 0 Hella is non-zero. People that know the, the topology of symmetry breaking, that is it. I leave it as an exercise, okay? It makes no sense that I do everything here. But I want you to appreciate this.
Okay. We could make all those choices, but can we relate them all by SU2 transformation?
Yeah, sure.
And then not worry?
Sure,
Well,
right. That's what you are supposed to do, right? Because what you do, okay, the simplest thing to reason is like this, okay? You reason like this, okay, he wants this. So I say, and it's an easy exercise, that there is a transformation that will take a few minutes. Find U that takes one to the other and stop worrying. That means that this U will rotate all the fields in this. So work with this, it's easier. This is going to be a mess. Imagine a photon is going to be a complicated function of these guys. W is going to be complicated. Charge will not be diagonal. But then what would you do? You would diagonalize that. So at the end, in order to, to make your living, you would do that, okay, precisely right. This is the same argument that it shouldn't worry you, but I see that it worries you. When we say that you choose the vector in one direction, that's you did in SO3. There's no difference. Choosing a vector in one direction is precisely as choosing the spin or field in the direction that you like. Complete analogy. So there was no need even, you could argue for me to speak at length. But if you are not sure, please check. So we'll work with this, and then please, you cannot then say I'm gonna then forget Vasif and stick to Goran. It's just a convention, and this is the most general situation you encounter. And we predicted that SU2 cross U1 is broken down to U1. by phi 0. So if someone asks you, why is photon massless? First, I don't know whether photon is massless. They ask you, why is photon massless? Well, I don't know, you can say. But if standard model is a good theory of nature, then photon has to be massless. Massless, it cannot have a small mass, because if I explicitly break SU2 plus U1, all hell breaks loose. I lose the goodness, the normalizability of the theory. Okay? I can't do that. So we are predicting that there will be a massless gauge boson. This you learn in your homeworks. Let's find it. I think we can do that in the next 8, 9 minutes, 10 minutes. I don't think lunch. Okay, anyway, I have a comment to make, but maybe the machine off. So, where do I get the gauge boson masses? Where my Lagrangian, I'm writing now piece by piece, has this term also. So let's calculate the original phi 0 square. D mu is 0. These are Pauli matrices. Phi 0, we know what it is, so I will get 1/2 from phi 0. Where is it? It's there. It's 1/2. There is G over 2, so that's another quarter. And then we have a matrix which looks like this. G A3 plus G prime B minus G A3 plus G prime B, G A1 minus AI2 G A1 acting with 0V. Everything squared. You know what I mean, Hermitian conjugate. I mean, this is a matrix, okay. Okay, I've just written the covariant derivative in its gory form. And this is 1/2, 1/4 times V squared. V will come out. By the way, I could have kept here V plus H just to know how Higgs interacts, okay? Remember where you see V squared, but we can do that later. There will be always V plus H squared. V squared, and then what I have is G A1 minus AI2, G A3 minus G prime minus sign, I keep it like this. This has to be squared. And this is 1. This is equal to 1/2 times 1/4 times V squared times A1 squared plus A2 squared plus G squared plus G squared plus G prime squared GH3 minus G prime B Let me see if you agree with me. The first element will give me G squared A1 squared plus A2 squared.
Yes.
Right?
Yes.
Here it is. This is G. And this is, I just normalized. Okay, this is the second term which is just normalized. There was this squared, I divided it and multiplied it by square root. I want to keep the normalization that I had before, so I normalize this field. Notice in the limit G prime goes to 0, what I get the same masses. So I ought to be right. Okay, G prime 0, they're all G squared times V squared, which was the old result. Okay, so that is whatever you compute, you stop and check with it. So what I learned here is the first prediction that MA1 is equal MA2 is 1/2 GV. This I'm going to call MW. And you may remember that W was a linear combination of A1 and A2. Remember when we wrote the interactions, we write it again. Anyway, and I found one more massive gauge boson, which I'm going to call Z. And in order to make the notation neater, I will introduce tangent theta W, which is G prime over G. That's called the weak mixing angle. We already defined it when we were looking in the theory without the heat mechanism. Remember what I did in the Glaciers model? I said, imagine there is a photon, and I predicted the Z boson. That's glacial. This is Weinberg's paper, if you read. It doesn't have to mention anything. This is coming out. There is a photon because one linear combination is massless, orthogonal to this. So that means that Z boson is, I'm not writing the Lorentz, to be simple, is cosine theta W times A3 minus sine theta W times B. That means, and MZ this is simply equal MZ cosine theta W. The Z bus is bigger by the ratio G square over G. That's cosine squared theta W. Okay. What is then photon? It's a field orthogonal to this. And there is a prediction, let me write in as a different in a capital letter. Photon is massless, okay. It came out. But it had to come out because I found that one direction of symmetry breaking remains untouched, okay. So this is the crowning achievement of the standard model. It turned out that this was a correct prediction once theta W was measured. You see, what I said, that the masses are almost the same, and the reason is that theta W is a small m. Not terribly small, but small, around 30 degrees, and that gives me cosine pretty large. Okay. In the first approximation, that's why you can remember it. They're basically the same, okay? And that's the limit. When you want to understand things, some topological thing, geometric thing, group theory thing, take the limit tangent theta W equal to 0, although it's not logically correct, right, to see that you are back in the SU2 simple picture. Okay. Obviously, if I had taken massive vacuum, I would see immediately that I get the same result. It would be more complicated with what we call LL vacuum. It will come out. I guarantee you that we will get the same prediction for the mass. For the guy will look great. But anyway, these are just rotated states on. Okay. I should let you eat. I know it's
No, that
this
one.
button.
It's this that one, yeah.